the last talk for this year and for this decade in the famous Rutgers University Experimental Math Seminar will be given by Timothy Chow from CCR in Princeton, who will talk about algorithmically distinguishing irreducible characters of Sn. Thank you. As usual, if you have questions, please unmute yourself. Otherwise, mute yourself and then unmute yourself to ask a question. And we hope to finish by 48 minutes, and the formal end of the talk and the recording will end after 50 minutes. But then everybody is welcome to hang around and ask informal questions to Tim. Thank you. Go ahead.
All right, thank you very much for this invitation to the Experimental Mathematics Seminar. I will say right away that there was indeed an experimental component to this research when we were figuring things out. I'm not sure how much of that I'll really be able to talk about during the talk, but I'll try to mention it here and there when I get a chance. Most of the talk will really be just an algebraic combinatorics talk. And Doron has emphasized to me that not everybody will be familiar with irreducible characters. So I'm going to start with some background just to explain what those things are. It comes from algebra, so I'll give an algebraic background. Although, in fact, in the end, we're going to be using a combinatorial definition, so you don't even really need to understand the algebraic definitions, but I think it's good to have some understanding of where it all came from. So it comes from the representation theory of finite groups. And a representation of a finite group is a homomorphism from the group G to the group of invertible linear transformations on a d-dimensional vector space. And D we refer to as the degree or the dimension of rho. And it doesn't actually have to be the complex numbers, but it's a lot easier with the complex numbers, and that's all I'll be concerned with today. So it's called a representation because G is an abstract group, but here you're actually representing the elements as matrices, D by D matrices, if you like. So a very important definition is reducible representation. So a representation is reducible if there's a non-trivial subspace, so not equal to 0, not equal to the whole space, that is invariant, meaning that it's preserved under any element of the group. And if rho is not reducible, then we say it's irreducible. And there's a theorem which I didn't bother stating on here, which says that every representation can be built out of the irreducible representations just by taking direct sums. So it's really the irreducible ones that we really want to understand. And another theorem is that for a given finite group, the number of non-isomorphic irreducible representations is finite. In fact, it's equal to the number of conjugacy classes of the group. So this finite list of irreducible representations gives you a lot of information about the group G. And group theorists are always very interested in this sort of thing. It's one of the first things they want to know about a new group that you present to them. So irreducible representations are defined this way. What about irreducible characters? Well, it's what you might expect is if you have a representation, you can take the trace of the matrix, and that's called a character. This is a complex valued function now. Instead of having a whole matrix to deal with, for every element of G, you just have a single complex number. And it might seem like you're losing a lot of information that way. Instead of a D by D matrix, you're just taking a single number, the sum of the diagonal entries. But it's actually, and the other thing is that the character value only depends on the conjugacy class of the element, because the trace is invariant under conjugation. So the character is constant on conjugacy classes. So it seems like you're losing a lot of information here. But there's a remarkable theorem, which again, I'm not going to prove, but if two representations have the same character, then they are isomorphic. So in some sense, the character actually contains all the information of the irreducible representation. And so the trace of an irreducible representation is called an irreducible character. So that's the object of interest for this talk. Now, this seems all very abstract. Later on, I'll actually give you a more concrete definition for a specific case of interest. This is all for any arbitrary group, but I'm only really interested in a specific group for this talk is the symmetric group, Sn, of permutations on n elements. So in this particular case, you might ask, can we write down concretely what these irreducible representations or reducible characters are? And the answer is yes. So to state the result, we need to define what a partition is. I think most of you are familiar with this, but formally a partition of an integer n is a weakly decreasing sequence, lambda, lambda 1 up to lambda L, of positive integers that sum to n. And the number of conjugacy classes of the symmetric group is equal to the number of partitions of n. Well, why is that? Well, for two elements to be conjugate in the symmetric group just means that they have the same cycle type. So really, conjugacy classes are enumerated by cycle types, but a cycle type is really just a partition. And I said earlier, I didn't prove it, but I said earlier that the number of irreducible representations of a group is equal to the number of conjugacy classes. So with that in mind, you might hope that the irreducible representations of the symmetric group are naturally indexed by partitions. You have the right number of them, and so you might hope that there's actually a bijection somehow, or a natural way to associate an irreducible representation of the symmetric group with any partition of n. And the answer is to that question is yes. So this is one of the fundamental theorems in the subject, that given any partition of n, you can indeed construct a corresponding irreducible representation. It's called a spect module. It's often written S lambda corresponding to it. And these are all the irreducible representations. They're pairwise non-isomorphic, and every irreducible representation is isomorphic to one of these S lambdas. And again, the character is just the trace. So if rho is a spect module S lambda, then we write chi sub lambda for the corresponding irreducible character. So these chi lambdas are what I'm going to be interested in today. So again, so for every partition lambda of n, this is just some complex valued function on the symmetric group. Now, as it turns out, in the case of the symmetric group, it's not just complex valued, it turns out to be integer valued. And so there's actually a nice combinatorial way of defining what these things are, which I'll get to in a moment. But let me just pause to make sure that everybody understands what it is that I'm talking about with an irreducible character.
A quick question. For an arbitrary finite group, do you ever have a non-rational entry values for the characters? With always rational numbers.
I'm sorry, could you repeat the question for an arbitrary group?
For an arbitrary finite group, are the characters sometimes complex numbers that are, for example, transcendental, or at least not algebraic, not rational, irrational? Or
No, yeah, they can be irrational. Yeah, they're not going to be transcendental, I don't think.
Yeah, so it's always
algebraic, yeah.
Algebraic, yeah, but not necessarily rational. Thank you.
But they could be irrational, yeah. Okay, so in particular, here's a basic question about irreducible characters of the symmetric group that I am interested in. Suppose you have two distinct irreducible representations of Sn. So they're indexed by distinct partitions, lambda and mu. Well, that means that they differ on at least one permutation of Sn. There has to be some pi in Sn such that they're different. But how hard is it to actually come up with such a thing? If I give you lambda and I give you mu, how hard is it to come up with some pi where these two values differ? Now, irreducible characters of the symmetric group have been studied for 100 years. So a lot of the questions that you might ask about them have already been studied, and they're either known or they're conjecture or they're hard. As far as I can tell, nobody has really asked this question before. I mean, maybe I've missed something, but I've asked a number of experts and looked at a lot of literature. It doesn't seem like this kind of computational question has been addressed before. So, I thought that was interesting, and so I decided to try to investigate this particular question. And one thing, like if you talk about experimental mathematics and you just try and play around with computations and see how hard it is, there's some sense in which it seems that it's easy, because in fact, not only does there exist one usually, in fact, lots of them, and maybe even most pi, these things are going to be different. So if you just try something, like first of all, you just try the identity permutation. The identity permutation works a lot of the time and suffices to distinguish two things. If it doesn't work, you could try something with just a single transposition, and often that works if the identity didn't work, and so forth. So usually, if you just try a few such things, it seems that it takes only a few tries to find such a thing. But I to this day, I've not really been able to prove this because the behavior of these chi's and chi lambdas is kind of complicated, as you'll see in a moment. And although this seems to be empirically true, it's not something that I've been able to prove that you only need to do 5 tries or something like that. I don't know if that's true. I can't prove it. It seems to be hard. And here's another indication that this might be a difficult problem. For example, you might ask, how hard is it to figure out whether or not this thing is 0? How hard is it to compute these things, or even just figure out that it's a non-zero thing? Well, this turns out to be NP hard in general. Like if you take an arbitrary lambda, arbitrary pi, and you want to know whether it's 0, this is not easy. I mean, for certain values of pi, like the identity or something, it's easy, but in general, this can become a very difficult problem. So you might worry that this is also a difficult problem. Fortunately, it turns out that the answer is actually, it's not that. It's not NP hard. So our main result can be stated, I think, most cleanly in terms of thinking about queries. So what do I mean by oracle access to a function? So suppose there's some function on the symmetric group. What does it mean to know this function? Well, one way is you list n factorial values, but n factorial is kind of a large number. And so you might think about, if I have oracle access to the function, it means that the only way you can obtain information is to submit a query. You can say, I want to know what the value of f is on a particular value pi. And the oracle will truthfully tell us the value of f of pi. So this notion of oracles is often used to try to understand when something seems like it might be hard because it's n factorial or something. You might try to simplify the problem.
Tim, it's really not n factorial. Probably there's a number of conjugacy classes, so it's just P of n, right? Because it's the same if it's conjugate. So
Sorry, say that.
It's not quite as n factorial. It's a number of conjugacy classes.
Oh, nice. Number of conjugacy classes.
So it's really P of n, which is not
That's right.
n factorial.
Yeah, it's still, you're right.
Yeah.
Yeah, because it's constant on yes, for characters, it's only going to be the partition number, which is still exponential, but yeah, it's less than n factorial. So anyway, you might try to say, let's set aside the question of how hard it is to compute pi, but if you're trying to find some particular value of pi, you might ask, how many values of pi do I have to try? And that's the first thing we were managed to figure out. We found there is actually this deterministic algorithm. So suppose you have oracle access to some function. So somebody comes to me and they say, I have this function f. I'm promising you this is some irreducible character, but I'm not going to tell you which one it is. And now you're going to play a game with them. You're going to say, okay, well, what is the value of your function on this partition or you know, this permutation or this conjugate class? What's the value of this? And then you have this conversation with this person, and you might ask, how many questions do you have to ask in order to figure out which one it is? And it turns out that that our main result is that you can figure it out with just our original analysis said n to the 3/2, but actually if you're more careful about counting how many queries you really need, Jiasheng Hu looked at our paper and said actually it's only O of n queries. And moreover, it turns out that okay, so if you have an answer to this, then you can try to solve the original. You can solve the original problem of distinguishing these two things by just running this algorithm on, let's say, chi of lambda. So now chi of lambda is not unknown, but you can just say, let me figure out what is the value of lambda. So let me try figuring out what it is on these different values of pi until I find something that distinguishes it from everything else. And so this will solve the original problem, with the catch, though, that I haven't yet said in this theorem statement that the values of pi are actually easy to compute. But it turns out if you look at the proof and you look at what queries we need, all the values of pi are values for which it's easy to compute this value, chi of lambda. You avoid the NP hardness result because you're only focusing on specific values of pi for which it's easy to compute. So in fact, the whole answer is that you can solve this whole thing in polynomial time. So that's our main result. And if you take away nothing else from this talk, if you zone out at this point and don't pay any attention to the rest of the half hour, this is the main takeaway, that there is an algorithm that will be able to answer this question in polynomial time, despite the fact that even computing chi lambda of pi in general is NP hard. All right, so let me now try to explain some things in more detail. So far, I've just defined this chi lambda in the abstract, and I haven't even told you how you would compute it on anything, let alone try to compute it on these particular things that are of interest. So let me get to something. I'm going to work towards something called the Murnaghan-Nakayama rule, which is a purely combinatorial rule for computing these characters. We've already talked about what a partition is, lambda 1 up to lambda L. And there's a standard way to draw a picture of it using Young diagrams. So you just have a left justified grid of boxes, and you have lambda I boxes in row I. So for example, if 7, 7, 5, 4, 1 is your partition, I have 7 boxes in the first row, 7 boxes in the second row, 5 boxes in the third row, 4 boxes in the fourth row, and 1 box in the fifth row. And I have a left justified. They're all lined up on the left. Okay. And a nice thing about this picture is that you can then read off what's called the conjugate partition of lambda. And this is what you obtain by just flipping along the main diagonal. Or alternatively, you can just think of it as the sequence of column lengths of lambda. So in this case, the conjugate would be 5, 4, 4, 4, 3, 2, 2, because those are the lengths of the columns. All right, so these Young diagrams are going to play an important role in what we're going to do next. And so far, everything I've said is completely standard. Now, here's my first definition that is maybe not completely standard, but it's going to play a very important role in this particular talk. So by the ith principal hook of a Young diagram, I mean, okay, here's a formal definition, but it's easier to see from this example what I mean. So the first principal hook consists of these red boxes. So I take all the boxes in the first row and the first column together. That consists of the first principal hook. And the second principal hook, well, it's the orange boxes. So I go inside, I take everything in the second row and the second column except what I've already used up in the first principal hook, and that's the second principal hook. And the yellow is the third principal hook, and the green is the fourth principal hook. So that's what I mean by principal hooks. And the ith principal hook length is going to be the area of the ith principal hook, or the number of boxes, if you like. So again, you just count the number of boxes here, and you'll see that there are 11 red boxes, 8 orange boxes, 4 yellow boxes, and 1 green box. So the principal hook lengths are 11, 8, 4, and 1. So I can already give you a general outline of how our algorithm works. What we do in order to, so remember, what's the algorithm? I'm talking with somebody who's got a secret partition, and I'm trying to figure out what partition it is. So what I'm going to do is I'm not going to figure it all at once. I'm going to ask various queries, and I'm going to figure out partial information and piece it together. So the first part of my algorithm is going to do what I call a forward pass, and I'm going to figure out what the principal hook lengths H1, H2, and H3 are one at a time. All right, so knowing the principal hook lengths actually already narrows down the possibilities for the partition a lot. But it doesn't completely define what the partition is, because just because you know there are 11 boxes in the first row and column together you don't know how they're spread. They could be slid around. The first row could have a lot of them, or maybe the first column has a lot of them. You don't know exactly. And even after you fix the first hook, the first column, the second one, there's some variation, there's some wiggle room there. But at least you got this during the forward pass. So in the second part of the algorithm, there's a backward pass. We're actually going to figure out exactly what the shapes are, exactly how the boxes are arranged in each of those hooks. And it's called a backward pass because we'll actually start with the innermost principal hook, and we'll figure out how that one should be arranged. And then we'll work our way back outwards and add one layer at a time and figure out exactly what the shape looks like. So this is maybe a little bit unusual because normally we think of partitions as being built up one row at a time or one column at a time. But for the purposes of the algorithm, it's important to think of them as one hook at a time. And you'll see that, we'll see why that is later on. And here's one more.
Tim, it is similar to the so-called Frobenius representation of a.
Yes, yes. Yes, you can think of it as Frobenius representation. Yeah, that's right. Where you think of like the arm lengths and the leg lengths. Yes, yes. But I like to think of it as, you know, the whole thing as a single hook for psychological reasons at least. And let me mention one other point about the backward pass, just to illustrate. So imagine that we have actually figured out that here's a partition with two hooks. Suppose that somehow we figured out that the second hook, not only is the hook length 5, but there's actually 4 boxes here and 1 box here. So that part is known, but we're not sure about the first hook. We know the total number of boxes, but we're not sure exactly how it's positioned. So it's equivalent to figure out how much of an overhang there is. So by an overhang, I mean the arm overhang is how many boxes are there in the first row that stick out beyond, you know, the next hook. And the leg overhang is how much, in orange here, is how much does the first column stick out beyond the first one. It might actually not stick out at all. The overhang could be empty. But in the backward pass, what's going to happen is we're actually going to figure out what these overhang lengths are. And that's how we're going to figure out how to position this thing. Okay. All right, that's just a general outline of how this algorithm is going to go. But I still haven't told you how to compute anything, right? So now I need to fulfill my promise to tell you, how do you actually compute these chi-lambdas? And you might think you need all this representation theory to understand that, but fortunately, other people have done that work for us. So there's a purely combinatorial rule called the Murray-Nakayama rule that will give us a recipe for computing irreducible characters of Sn. And this looks a little bit strange. I mean, I could have just defined irreducible characters using this rule. In fact, it'd be completely self-contained. I wouldn't have to talk about algebra at all. But then it would seem like, where is this thing coming from? So I didn't want to do that. I want to give some background. But here, I'm going to tell you exactly how to compute these things without actually needing to know any representation theory. So to understand this Murray-Nakayama rule, we first need to say what a border strip is. Some authors call this a ribbon or a rim hook. Well, I like to call it a border strip. And a border strip is a finite set of boxes so that in each row, the boxes in that row are contiguous, so they're all connected together. And in every row, the rightmost box of that row lies directly underneath the leftmost box in the row above it. So I think of it as I write down however many boxes I want in the first row. And then for the second one, I put down a box that's just beneath the leftmost box above, so like here. And then if I want, I can stick some more boxes to the left of that. In this case, I decided not to. I just put one box. And then I decided to go to the next row and put a box there. And now I decided, okay, I'm going to put a couple more boxes to the left here, and so on. So the only condition is that each row's rightmost box has to be directly underneath the leftmost box of the one above it. And so here are some more examples of border strips here. 4 examples. They're necessarily connected just by the way I've defined them. And by the area of a border strip, I mean the total number of boxes. So, you know, the area here is 1, the area here is 7, and so forth. And another important quantity of a border strip is called its height. So the height is the number of rows minus 1. So in this case, the height is 3, 2, 0, and 3. Okay. And I'll write the height as h of b. All right, so one more definition here. A composition is just like a partition. A composition of the number n is just like a partition. So it's a sequence of numbers that add up to n, except that I'm not requiring it to be weakly decreasing. It can be in any order, but it does have to sum up to n. And now here comes the most crucial definition of the Moorhead-Nakayama. It's a border strip tableau. So if I'm given a partition of n, which is the shape of this Young diagram, and alpha, a composition of n, then a border strip tableau of shape lambda and type alpha is a tiling of this Young diagram of alpha. And it's tiling this Young diagram with border strips. So the individual tiles have to have this border strip property. You can't put down a square, for example. That's an illegal tile. The only legal tiles are border strips. And furthermore, the area of the ith border strip should be alpha I. And here's the most tricky condition. If you write down the number I in every box of the ith border strip, then the numbers have to weakly increase across every row and down every column. So let's take this example here. So here I've taken this partition lambda 5, 4, 4, 1, what we've seen before. And now let me take a composition here of n, 4, 5, 1, 1, 3. Okay, so that still adds up to 14, but not necessarily, in this case, it's not weakly decreasing. So what does it mean to have a border strip of shape lambda and alpha? So now I have to tile this Young diagram with border strips where the first border strip is size 4. And so those are the red things. Those red things, that's a border strip. And 5 here is the orange. I put those 5 things. It's got 5 boxes in that border strip. And then 1, 1 for the 3 and the 4. And then 5, the 5th border strip has to have 3 things. The colors here, by the way, are not actually important. They're just for visual clarity. But the second condition here means if I write the number I in the ith border strips, I put 1s in the first border strip and 2s in the second border strip and so forth, then across each row and down each column, these numbers weakly increase. Okay. So for example, if I had tried to put these 1s, that border strip over here on the right, that would not really work, because that would mean that some of the larger numbers would be over here to the left of it, and you would violate this weakly increasing condition. So in fact, the border strip, the first border strip has to contain this upper left corner in particular. Okay, so is that clear what the definition of a border strip tableau is? Okay, so the Moorhead-Nakayama rule now is we're ready to state it. So if lambda is a partition of n, and we're trying to figure out what chi lambda is, well, we're trying to evaluate it on some particular permutation, or in other words, some particular cycle type. And so if alpha sub I is a sequence of cycle lengths of pi, then chi lambda of pi is the sum over all border strip tableau of shape lambda and type alpha. And then now you have this product. You take the product over all the border strips in the tiling, and you take -1 to the height of B. Remember, this is the number of rows of B minus 1. Okay, so that's the formula, and I'll go through an example in a moment. But right away we can see.
Tim, what if you don't have the minus? Then you have an integer 6. You have an integer, another kind of integer, bigger. Does that have any significance without the -1 to the power? That's the sum of all these guys.
Oh, that's a good question. If I change this -1 to 1, yeah, I don't know. I don't think it has any algebraic significance, but I don't know if there's any combinatorial thing.
Be interesting to see if it's an OS. I mean, if we add them up.
Yeah.
So can I ask you something? The alpha, that's a composition, right?
Yes.
Okay, thank you.
Yeah, so that's a good point here. So let me yeah, so you might say why not a partition? It's a composition, but I'll come back to that in a moment. But let's do an example here just to make sure we know how to parse this definition here. So let lambda be 5, 4, 2, okay? And let's say alpha is 6, 3, 2. So here it actually is a partition, but that's fine. So let's try to figure out how to figure out this formula here. So we got to figure out what all the border strip tableau are, where there are 6. You know, the first border strip has 6, the next border strip has 3, and the next border strip has 2. So so I've drawn 2 examples here. So the 1 has size 6, and the 2 has size 3, and the third one has size 2. And I've done it another way here, and we can see that the things are weakly increasing across the rows and down the columns. Now, is that all? Okay, well, you'd have to sort of check this. But for example, you might wonder, why can't I put the ones, like have the first 3 things, all 3 things in the first column be 1s, and then, you know, just go all the way up to this point and have those be my 6 1s. The trouble is now there's this box here on the edge which is isolated from the other things, and you can't connect it. I mean, the only way you could tile it would be with a border strip of size 1, but you're not allowed any border strips of size 1. So in fact, you cannot do that. And similarly, the border strip of size 1, can you avoid using that top left? No, because if you did, then there would be something larger there, and it would violate this weakly increasing condition. So really, this is the only way to place the 1s. And once you place the 1s, again, there's only these 2 ways of placing the 2s, because if you try to place the 2s like this, you know, then you cut off these 2 things from each other. They wouldn't be a single border strip anymore. And that would not work.
I thought, Tim, in your previous slide, didn't you have a border strip of size 1 marked 3 on the previous slide?
Yes. I mean, there's nothing wrong with border strips of size 1 in general, but here we've got an alpha that's 6, 3, and 2. So the requirement is that we have to follow the alpha that we're given. We have to have a border strip of size 6, border strip of size 3, border strip, yeah. Because
okay, so another question is, you say suppose alpha I is the sequence of cycle lengths of pi. What does that mean? I mean, pi is just, do you take them in order? How do you define the cycle lengths?
Very good, very good. We'll come to that on the next slide. So yeah, I mean, permutation, there's no canonical ordering to the sequence of cycle lengths, right? Why did I take them in 6, 3, 2? Why didn't I take 6, 2, 3? You know, what would have happened if I changed them? Okay, we'll get to that in the next slide. But for a moment, let's just finish parsing this particular thing. So these are the only 2 border strip tableau. So the sum is over 2 things. And then what's this product thing? Well, on this one, it's the product of all these minus 1s to the heights. So the height of the 1s is 1, the height of the 2 is 0, and the height of the 3 is 0. And over here again, it's height of the 1s is 1, but now the height of the 2s is also 1, and then the height of the 3s is 0. So after all that, we find that this cancels out, and the value of this character at pi is 0. Okay, so this is saying that if the cycle lengths of pi are 6, 3, and 2, then chi of lambda with this lambda is actually 0. Okay, but now let's get back to this question. Well, what if I had taken a different, like if I had taken some pi with 6, 3, and 2, I could have taken 2, 3, 6, or, you know, and doesn't that give you a totally different thing? Well, yes. I mean, let's see. Yeah, okay, so I just recopied what I had on the previous slide so that we have it on the in front of us. But now, let's suppose that I had taken 6, 2, 3 instead. I mean, why not? Cycle lengths, I'm listing them. They don't have to. There's no one telling me I have to listen to 6, 3, 2. Why not 6, 2, 3? And now what we'll find is that, in fact, there's no way to do this. There's no way to actually do 2 2s, you know, have the 2s be a size 2 and then the 3s be a size 3. Because if you try to do that, for example, if you try to make these yellow things 2 and the orange things 3, that would violate this non-increasing thing. And similarly over here, you'll conclude that there are no border strip tableau of that lambda type alpha. Well, that's okay. I mean, then you have an empty sum. So chi lambda pi is 0. So that's kind of a magical thing about this Moring-Nakayama rule. Even though you get different combinatorial things popping out when you rearrange these alphas, they always give you the right answer. So you're free to actually choose whatever ordering you like that suits your fancy or suits your purposes, and you'll still always get the right answer. So that's kind of a part of the theorem, which is a little bit magical. Does that answer the question?
Tim, are we still in James and Kerber, or is this more recent stuff?
I think this is in James and Kerber. It's I think it is. I mean, I always learn these things from Bruce Sagan's book, but this is pretty old. I'm pretty sure it's in there. I can't swear to it, but this is definitely a very old thing. Does anybody out in the audience happen to know the answer to that question? It's actually in James and Kerber.
It's in the McDonald's book probably also, isn't it?
Yeah, I'm not absolutely sure, but I would be surprised if we were. It's not that recent. Okay, so from now on, instead of taking permutations as our queries or even partitions, we're going to allow ourselves to take compositions. So these are the things that we're going to be asking about. What is the value of chi lambda on a particular composition? All right, so now let's go back to our original problem. We're talking to this person who has a secret lambda, and we're trying to submit queries to figure out what's going on. So here's the key observation. Suppose there's some there's a shape lambda, and I now submit a query alpha with a very large alpha 1. In fact, I take my alpha 1 to be larger than the size of the first principal hook length, the principal hook length of size 1. So in other words, I ask for an alpha 1 that's bigger than the total of the first row and the first column. Well, I claim that there cannot exist such a thing because the first border strip just doesn't fit, just can't possibly fit inside this Young diagram. It's too big. The most you can do, most you can accommodate would be to use up the entire first row and the entire first column. And if alpha 1 is bigger than that, there's no border strip tableau. And therefore, the answer is going to come back, the value of this function, chi lambda, is going to be 0. All right? It's an empty sum. So that gives us a hint as to how can we figure out what is the size of the first principal hook. What is the first principal hook length? So suppose n is 10. So we don't know lambda, we just know it's a partition of 10. And we're trying to figure out how big the first hook is. So we start asking this person, well, what about if I take alpha just to be 10? There's a single part of size 10. And if the answer is 0, well, we've learned something, because now we know that the first principal, well, sorry, if it's non-zero, we know that, okay, so if, if I said it backwards here. So if in fact the first principal hook is less than 10, then the answer is going to come back 0. All right. And so if we hear that, we can then go on to this next thing, 9, 1, and 8, 1, 1, and 7, 1, 1, 1, and so forth. And so if alpha 1, as long as we're actually asking for these alpha 1s that are bigger than that thing, we're going to get zeros. So typically what's going to happen is we're going to get a bunch of answers 0, 0, 0, and then all of a sudden, maybe we'll get something that's not a 0. And I claim that when you hit the thing that's actually correct, when you actually guess the correct H1, there will actually be, you'll actually get a non-zero answer back. Because what we're doing here is we're saying, with 1, 1, 1, 1, 1, we're saying just fill in the rest of whatever you got there with single boxes. And you're going to get border strips that fill in those things, and they'll all have the same sign. So let me give an example here to make it clearer. So suppose n equals 11 and lambda is this 5, 4, 2. And we know n is 11, but we don't know what this thing is. So H1 in this particular case is 7. So what's the recipe I'm saying you suggest? Well, I'm going to ask I'm going to first ask, okay, what if my composition is 10? I want to have a border strip with a thing of size 10. Well, that doesn't work. It's not going to fit, so it comes back 0. So then I try 9, 1. That's also going to come back 0. 8, 1, 1, 0. And then finally now 7, 1, 1. Okay, 7, 1, 1, 1, 1. What's going to happen here? Well, now the 7 does fit here. And what about the rest of it? Well, yeah, you can certainly fill up whatever's left with singletons, right? So the only thing you have to worry about is, well, maybe these things will have different signs because the Nakayama rule has signs, and maybe these will cancel out. But the point is that singletons always have height 0. So no matter how you rearrange these things, there may be many different ways of rearranging these singletons. They're all going to have the same sign. And the heights are all the same, even though they've shuffled around in position. So in fact, all these border strip tableaux will have the same sign, so they'll reinforce each other, so we'll get something non-zero. So that tells us as soon as we hit something non-zero, we've actually hit the correct thing. So this sequence of queries lets us know what the size of the first principal hook is, because it's the first non-zero thing we get in that sequence. All right, well then what about the next principal hook? Well, now that we know the size of the first principal hook, what we can do is we can freeze that. We can take our alpha 1, the first element of our composition, to be the H1 that we know, and then we apply the same trick for the next largest part. So like if we figured out that H1 was 10, then we try, and N is 20, then we try 10, 10, 10, 9, 1, 10, 8, 1, 1, 10, 7, 1, 1, 1. And again, I won't go through the whole argument here, but you will find that as soon as you hit you'll get zeros until you hit the actual correct value for H2, and at that point you'll get something non-zero. So then you'll know what H2 is, and so forth. So you can recover what the values of these H's are. And just as a comment, I'm not going to. This is really for the experts who know how hard is it to actually compute these numbers. There's a hook length formula that's easy to compute, so you don't have any NP hardness problems with computing these values. The hook length formula gives you an easy to compute value here. All right, so this gives us a simple algorithm for figuring out what the hook lengths are. But now, what about the backward pass? So we actually need to figure out how these hooks are arranged and not just what their lengths are. And so, as I said before, you start with the innermost principal hook. And it turns out that by an inductive argument, you can just reduce to the case where you know the whole shape, but you're just not sure about the first principal hook. Again, I'm going to skip that inductive argument, but it really does reduce to this special case. You're moving backwards, and if you can figure out how to recover the first principal hook, knowing everything else and knowing what the first principal hook length is, but just not knowing what the arm overhang and the leg overhang are in the first principal hook, then this is what you actually need to figure out. So it seems like it's a pretty small problem, right? I mean, there's not that many partitions. We reduced it to a small number of partitions. But this actually gets a little bit tricky. And since I do have some time, I'll tell you a little bit here about how this works. So one important lemma to know is that a border strip in a border strip tableau cannot contain more than one box on the principal diagonal. Okay. So why is that? Well, suppose the border strip contains I, comma I, you know, the box in position row I and column I. Then just think about the definition of a border strip, right? So this is in some row of the border strip. And so just visualize that it's in some row of the border strip. Well, how could you have J, comma J with J greater than I? Well, this would have to be a lower down row. And it would also have to be to the right of I, but that's not allowed. The whole definition of border strip is everything lower down has to be either directly beneath or to the left. So there's no way you can actually reach J, comma J with J greater than I if you start at I, comma I. So this tells us that a border strip cannot contain more than one box on the principal diagonal of your Young diagram. And so from this, you can deduce that for all K, the first K border strips must be contained entirely in the first K principal hooks. So this is an induction on K. So let me just give you an example. So suppose here, you know, you have figured out that the first border strip is entirely contained in this. I mean, if the first border strip is contained in this first principal hook, what about the second border strip? Could the second border strip contain something out here that's not in the first two principal hooks? Well, the thing is, if there's a 2 here, then like everything up and to the left has to be a 2, right? Because by the non-decreasing, I mean by the weakly increasing thing, you can't have anything larger than 2 in this region, because that would violate the weakly increasing condition. So all these would have to be 2s. But then now you would have 2 boxes in the principal diagonal that are both 2s, and that would contradict lemma 1. So in fact, these border strips have to kind of be packed from the top left going in, and you can't kind of cheat and jump ahead. The first 2 border strips have to be contained in the first 2 principal hooks, and so forth. So that limits the possibilities here. And so what happens is, I think I'm going to have to skip through this a little bit quickly because we're running out of time. But it's similar that you can run through a bunch of queries where you fix all these other things, which you know, and you just try changing the values of these first two queries until you get something that's non-zero. So let me just give you this one example. What happens is I'm trying to figure out like what this overhang length is here. So here is overhang by 2 and overhang by 3. How do I know it's not overhang by 4 or something like that? Well, the thing is, if I make this first border strip too large, the second border strip, the first 2 border strips have to fill up these sections here. So if I try to create an if I try to say like my alpha 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9 here, and my alpha 2 is 1, 2, 3, 4, 5, 6 here, it's not going to work, because if the first one is too large, it's going to block the inner one from being able to reach these things. It's going to be a disconnection problem again. So the amount of the maximum size that this first thing can be without blocking this thing from reaching the first column is going to tell me the size of these overhangs. So anyway, that's a little bit fast, but let me just leave it at that. You just look at the geometry of these first 2 things, and that gives you a way of figuring out what these 2 things are. Okay, and then which overhang is which? You might, now you can, with this argument, you can figure out that there's an overhang of length 3 and the overhang is length 4. But which one's the arm and which one's the leg? This turns out to be a very complicated thing, and this is sort of where the experimental mathematics came in. Like, it seemed like we were almost done, but then we had to figure out exactly how do you figure out whether one's the arm or the leg, and we had to do lots and lots of experiments and had to solve on a case-by-case basis. It's kind of ugly. I'm hoping that someone else can actually figure out a better way to do this. But in the general strategy is still the same. Instead of taking permutations with lots of fixed points, which might be your first inclination, you actually take border strips with very large parts that kind of barely fit, and they block each other, and so that there are very few border strips possible, and then you analyze what that means and deduce what the partition must be. Okay, so concluding remarks, is there a more efficient algorithm? I still like the idea of trying to go back to permutations with lots of fixed points, and so then you're led to consider these generalized hook length formulas, and so there's some hope that you could do this because there are these formulas, but you have to kind of make sure that you don't get accidental equalities. Like you have this hook length formula plus this length formula minus that hook length formula, and they don't accidentally cancel out. So you have to be careful there. And I don't know how to do that. But if it could be done, then the number of queries could be reduced maybe even to a constant number and not just O of n. So I think that would be really nice if somebody could figure out how to do that. Okay, thank you very much.
Yes, thanks. This ends the formal part of the talk. Anybody who has to leave, welcome to leave. But people who want to ask more questions, and please, Robert, please stop recording. People who have questions can stay as long as they wish.